All right, ladies and gentlemen, welcome to your video lesson for 4.2, Constructing Arithmetic Sequences. Today we're going to talk about writing functions, but remember we're going to talk about how that language has shifted to, when we talk about sequences, we're now going to be talking about writing that explicit rule. And we're going to be writing that explicit rule from sequences that we see, but then also from real life examples that we see. All right, so let's get our warm up done here first, getting our minds in that mindset of sequences. So let's write the first four terms of the sequence. And so in the first one, we are given an explicit rule, and it looks like a function because, well, it basically is, right? So when we do this, we want to start, we talked about last class, how we want to start with the 0th term, okay, which means we're going to substitute 0 in for n. So these are n values, right? And then we're going to figure out what f of n is for each value for f of n. Remember we talked about how these were term numbers, and these were term values, respectively, values, right? So if I substitute 0 in, negative 4 times 0 is 0, plus 2 is 2. I substitute in 1, negative 4 times 1 is negative 4, plus 2 is negative 2. Then I substitute in 2. Negative 2 times 4 is negative 8. Plus 2 is negative 6. And then my fourth value that I'm finding, which is really the third term, right? I always substitute in 3. That would be negative 12 plus 2, which would be negative 10. Okay, now this is a setup for an explicit rule. It's printed in your notes, recursive rule. This is a setup for a recursive rule, which we decided this year to not delve into. So it's in your notes, but we are not going to talk about it, and you will not be held responsible for knowing. All right. Now, for the next one, last class, remember we talked about how we can use our explicit rule or our function to find any term in the sequence, and this is an example of that. So if I want to find the 25th term, remember what we do is substitute that in for n, because n represents the term number, right? Term number is n. So if I want to find the 25th term, I substitute that in for n. And remember, it actually kind of goes in two places, right? It's f of 25, which is a function evaluated at 25, but again, it's telling us the 25th term. And again, notice it went in right here. Negative 4 times 25 is negative 100. Plus 2 would be negative 98. And so we can say that the 25th term is negative 98. Okay? And then we can also flip that around, right? Well, what if I know what the 25th term is, right? But I don't know that it's the 25th. I want to figure out what term number it is in that sequence. Well, where does it appear in the sequence? So that's what this question's about, okay? So it says negative 122 is a term of the sequence generated by this function. It says which term number is it? Well, that means that this negative 122 is going in for f of n, right? Not in for n, for the whole thing, okay? And then we solve for the term number, right? We solve for the term number so we can figure out what term number it is. So negative 122 is put in for f of n here. And then I just solve that for n. So what's happening to n? I'm multiplying by negative 4 and I'm adding 2. Last thing I said was add 2, so I'm going to subtract 2 from both sides. I should have been subtracting 2. I made a mistake. I was kind of doing this quick beforehand. Which means that this is negative 124, not negative 120. And so that means that this is, if I divide by negative 34, that means that this is 31, not 30. So I can say that the 31st term is negative 122. All right, so now that we got our warm up out of the way, let's talk about today's lesson about constructing arithmetic sequences. I gotta grab my pen here. All right, so one of the things we want to talk about is what exactly is an arithmetic sequence, right? You kind of already know what they are, you just haven't put a name to them yet. So let's look at this. It says you can order tickets for a local theater online. There's a fee of $2 per order, $2 per order. So if I make any order of anything, right, they charge me $2. And if I order a matinee, it's $10 each. The total cost in dollars for ordering n matinee tickets online can be found by using C of n is equal to 10 times n, 10 times the number of matinee tickets, right? Plus 2, and that $2 is just the fee to like convenience fee or whatever you want to call it, right? It says complete the table of values for this function. So we're going to figure out what the sequence is, right? So if I buy one ticket, that means I substitute 1 in for n, right? So 10 times 1 is 10, and I add 2 for the convenience fee, that's $12. If I buy 2 tickets, right, 10 times 2 is 20, plus 2 is now 22. And then the next one will be 32, and the next one after that would be 42. Okay, so it says find the difference between each of the 2 consecutive terms in the sequence. Well, the difference would be subtracting, right? So 22 minus 12 would be 10. It's going up by 10 each time, right? And we can probably guess that by this value in the function right there. So we're multiplying every ticket we buy by 10. So it's going up by 10. So the difference is 10. I'm going to call that D because later on we're going to call the difference 10. So D is equal to 10. Okay? So some definitions here. First of all, what's an arithmetic sequence? Well, an arithmetic sequence is a sequence in which the difference between each consecutive term is always equal. So let's look back, right? The difference between each of these terms was 10. So this is an arithmetic sequence. Arithmetic sequence means that the common difference is always the same. So they're always like counting up by 2s. 2, 4, 6, 8 is an arithmetic sequence because we're counting by 2s. Counting by 3s, counting by 4s. In this case, we're counting by 10s. Okay. So arithmetic sequence is a sequence in which the difference between the consecutive terms is always equal. The common difference is the difference between the consecutive terms that are equal, and it is D, right? Like I said earlier, it is that variable D, okay? So the table shows the number of plates left at a buffet after n hours, right? So I added a little bit of information onto your table here. I don't believe you have this 0 here. Maybe you do. But I added it on mine because I didn't have it. And we're always going to be working with this from the 0th term, okay? So like before anything happened, what did we have, right? That's what we're talking about, okay? So if n represents hours, at 0 hours, it's like how many plates did we have, right? Before anybody took any. And after the first hour goes by, we have already lost some plates. We're at 155. And the second hour goes by, we're at 141 and so forth, right? So our job is to first find the consecutive difference here, or the common difference. So I'm going to take the 155 and I'm going to subtract 141, and I get 14. Okay? And if I subtract 14 again, 144 minus 14, I get 141, 141 minus 14. That gives me 127, so I know that this is the same common difference. If I subtract 14 again, I do get 113. And so what's happening, right? What's happening is every hour, 14 plates are getting used. So now how do I go back and find the 0th term? What did we originally, how many plates were out there before people started coming to eat? Right? Well, if I'm subtracting 14 to go this way, I have to add 14. So 155 plus 14, that gives me 169 plates is what we originally started with. Now, when I write, we're not dealing with the recursive part, so I have it crossed out here. When we write an explicit rule for this, it's really just like an equation. Okay? It's going to be in function notation. So we're going to have f of n is equal to how many plates did we start with at time 0? What's 169, right? And how did those plates change? Well, we dropped 14 plates. I suppose I should probably put negative signs here, right? We dropped 14. We use 14 plates every hour, right? Well, if n represents hours, that means I'm going to subtract 14 every hour. And that would be my explicit rule, okay? So let's look at a couple of examples here. Hold on a second. All right. Next one here. The table shows the monthly balance of a savings account with regular monthly deposits. The savings account begins with $2,000 and $500 is deposited each month. Okay, so it tells us it begins with $2,000. That means at time 0, before any month's passed, I have $2,000 in the bank. After the first month, now I got $2,500. So again, if I'm going to write an explicit rule, I got to think, well, where did I start? So f of n is going to be, and n represents months here, right? The function of months for this, right, is going to be equal to my original $2,000 that I had. And now I'm adding to that how much? Well, 500 every month. So it's be 2,000 plus 500N. Okay. Now you might be saying to yourself, Mr. Fessbach, this is no different than what we were doing before. And you're right. Again, remember, we're only talking about a language shift here. Okay. This is then going to generate a sequence, which in this specific case, we can call an arithmetic sequence, right? So we generated an arithmetic sequence with this function, and then previous classes, before we got to module 4, we would just call this a function, right? We maybe would call it discrete because, in between the months, we wouldn't make any deposits. And therefore, again, it's just like a language shift here, okay? All right, the table shows the monthly balance of a savings account with regular monthly deposits, okay? So now we're given a little bit less information, right? But we're given in the first month that we have $6,000 and then $7,000. So we're depositing, right? Which generally means, well, it does mean that our values are going up. And so the thing that we have to figure out is what the common difference is, right? In that last problem, we were given that, right? We were given 500, we were given the starting amount. In this one, we're not given any of that. So the first thing we want to figure out is the common difference, because I can't figure out that first term. I don't know what that first term is if I don't know how much to go back by, right? So what's the common difference? Well, if I go from 6,000 to 7,000, that's plus $1,000, right? And then I'm adding $1,000 again, and I'm just going to complete this because I want to, adding $1,000 again, right? So that is my common difference. That's that value of D. So that means if I want to go back to the beginning of time when this bank account was formed, okay, I have to subtract $1,000 to go to month 0. And at month 0, before I started making deposits, that would be $5,000. Now when I go to write my explicit rule, it's going to be f of n, where again, n is equal to months. I have $2,000 in the bank. I'm sorry, I said 2,000. I think it's 5. Yeah, 5. Sorry about that. I think the last problem was 2,000. That's where I got screwed up. Oh boy, got to redo that. F of n is equal to 5,000. And then I'm adding to that amount, how much? $1,000. And how am I doing that? Every month, okay? So that would be my explicit rule that would then generate this sequence, right? If I substitute in, and I can find any, like if I want to know how much I have in the bank after 37 months, or 36, let's just say 36 months, because it's 3 years, then I would figure out, substitute 36 in for n, and then that would be the 36th term in the sequence. But then in the relation of, or in the context of this problem, it would be like, that's how much money I have after 3 years. Okay. So again, it's just a language play. So now we're formally giving you what the general explicit rule looks like, right? And it's what we were doing all along. It's that very first beginning of time amount, right? Before anything actually takes place, before we do the first thing, before the first month goes by for a deposit, before we make that first purchase or whatever, right? Well, like our actual starting amount. And then we add to that or subtract, right? It should really be plus or minus the common difference. I suppose we could say if it's just like always adding, we can just say it's always adding, and then the common difference could be negative, right? That would be fine. And then we multiply that by how many times we do whatever the thing is, right? And sometimes there's context to this and sometimes there's not. Again, we're not going to be doing the recursive rule. This is what it looks like. It's really not that hard, but we're just kind of taking some things off the plate. And so we're asked to write a general explicit rule for each of these equations. So the first thing I have to do is find my common difference here, right? So boom, my common difference. This is going to be going down 12. This goes down 12. This goes down 12. So my common difference is 12. So this is the first term. I actually have to find now these 0th terms. So which one goes here? Before we did a thing, we subtracted 12 first of all to get here. Now we have to find the first term. So I actually have to add 12 to go back. So then I would write that f of n would then be equal to that starting value of, I would have to add 12, right? To go back, which would be 112. So 112 plus, and it's negative 12. That common difference is negative, or you could write minus 12. And then times however many times we do the thing, right? And that's going to be n. All right, so the next one, same thing. This is my first term. I want to define everything as the 0th term. So I have to go back and figure out what this is. So the reason that first thing I got to do is figure out what is the next, or my common difference, right? So I'm going to add 8 plus 8 plus 8 and add 8. So everything is added 8. It checks out. So then I got to subtract 8. So my first term is actually, my 0th term is negative 8. So what I say is that, excuse me, moving myself around here, is that f of n would then be equal to that negative 8 plus my common difference, which is positive 8 times n. And then that would generate my sequence. Notice if this was the first term that we're given, right? Let's just make, like, some of you might be thinking, like, why in the world are we going back? Well, if this is the first term that we're given, that means we're going to substitute 1 in for n. To do that, right? So if I substitute in 1 for n, so f of 1 would be then equal to negative 8 plus 8 times 1. Well, 8 times 1 is 8 plus 8 would then be equal to 0. And that is the first term that we have, right? And it would work out with this one as well. So that's why we're going back to 0 when we define these, okay? So it works out. Same idea here. I'm just going to kind of whip through these. Common difference here, going up by 10, going up by 10, going up by 10. So that d is equal to 10. Now I can write my recursive rule. Again, we're not doing, I'm sorry, we're going to write the explicit rule. We're not doing the recursive rule. And f of n is then equal to the first term. I have to go back in time now, right? So what one really goes here? So I have to have 10. I have to subtract 6, would be negative 4. Okay, so negative 4 plus, and then 10 times however many times I do it, which would be n. Right? And again, just to prove to you, so we can get the first term, this would be 0. This would be the first term, right? I want to get 6 for the first term. I would substitute in 1, and negative 4 plus 10 times 1 would be equal to negative 4 plus 10, which would be equal to 6, right? And lo and behold, we do get that as our first term. So it works out. But this is the function. This is the explicit rule. Same thing here. Common difference, minus 2, minus 2, minus 2, minus 2. So we're subtracting 2 each time. So d is equal to negative 2. My function would then be equal to f of n. I got to fill in that first term, right? So how do I go back? I would have to add 2. So it's really 0, right? So this would be the 0th term. This would be the first term, okay? So the 0th term is 0 plus, and then it would be negative 2 times n. And again, just to check it out, we're just going to talk through this one. If I substitute in 1, negative 2 times 1 is negative 2, plus 0 would be negative 2, and that is my first term. So I get it when I substitute in 1. So it does work. We do, though, however, always have to go back and find the 0th term, and then that is what goes in this box, right? And then that's what this general rule says. F of 0. What is the 0th term, okay? All right, last example here. It says Jerry collects hats. Okay, good. I just want to make sure I didn't skip anything. All right, Jerry collects hats. I'll move myself. Boom, boom. I don't know where to go. Whatever, let's go here. All right, so Jerry collects hats. The total number of hats in Jerry's collection depends on how many years he's been collecting hats, which makes sense. After the first year, Jerry had 10. Each year, he has then added the same number of hats to his collection. Notice it doesn't tell us what that is, right? So we got to figure that out. We're not given a table, we're given a graph. So we're going to have to read the graph to figure that out. So the graph shows the sequence. It says write an explicit rule and function notation for the arithmetic sequence. So again, we know that it's an arithmetic sequence, so we're adding a common difference. We just got to figure out what that common difference is. So X represents time in years, and Y represents the hats here. What I have to do is figure out the difference in the height from each point, right? So how do I go from here to here after, well, this would be 1 year, right? And so in 1 year, I went from 10 hats to 8 hats, and then from 8 hats to 26 hats, and then from 26 hats to 34 hats. So I'm thinking that my common difference is 8. Every year we go up 8. So, I can just even show you that 18 minus 10 is obviously equal to 8, right? So then d is equal to 8. So my function would then be f of n is equal to, well, what would that 0th term be? Well, I got to go back in time. Okay. If I were to write out this sequence, it would have 10 and then 18, right? And then 26. And I would have to go back and figure out what this 0th term is. And if I'm adding 8 to get to each one, that means I have to subtract 8 to go back to get this one, which would then be 2. So my starting point, my 0th term would be 2, right? And so what this basically means is that at the very beginning, before he actually started collecting, is that Jerry had 2 hats, right? And then once he started collecting, he added 8 hats per year to his collection. So I just kind of answered the next part, right? So what are we doing? We're adding to those hats 8 per year. N represents years. I should say N equals number of years. And there we go. That's it. I can use this function if I want to figure out how many hats Jerry has after 30 years, right? I would just take 30 times 8, add 2, boom, done. All right, ladies and gentlemen, that is your lesson for today. I hope you guys are doing really well, and man, do I look forward to seeing you sometime in the future. Take care.